Welcome guys to another video on dynamic programming, and today we're going to be talking about DPV 6.28 local sequence alignment. And in this case we are given two DNA sequences which are significantly different, but they contain some regions that are very similar and highly conserved. And we have to design an algorithm that takes the input strings, which are X and Y, and then a scoring matrix, and then it outputs substrings x prime y prime inside these sequences that have the highest scoring alignments over all pairs of such substrings. And the algorithm must run in order m in time. And so the problem is very similar in a way to the earlier problem, which was 6.27 alignment with gap penalties, but there was global alignment, so you could even go back further to 6.26. And 6.26 is um, the case where the alignment was using simple um, gap uh, alignment and not the affine gap alignment as in 6.27. So let's look at how we will approach this problem. And this solution, if you want to look through Wikipedia, the solution is commonly referred to as Smith-Waterman, and it's a slight variation on the Needleman-Wunsch algorithm that we saw earlier in the earlier videos. So um, how is this different from the earlier global alignment method? So um, the major difference that you see is that we take a max when we try to fill a column. We come from three different directions. We come from this direction, we come from this direction, and we come from the match mismatch dimension, right? And two of these are just insert deletes, also known as indels, and then you come through the match mismatch dimension, which is this dimension, and diagonally. So those are the three solutions, but in this case, in the Smith-Waterman algorithm, you introduce a zero, and the max of this becomes the answer. So if there is negatives, then the negatives are suppressed by a zero, and that's the major difference. So for right off the bat, the initialization, remember that when we used to initialize this, we start off in this corner where there was gap and gap. And by the way, if you're not following this, I would highly recommend that you go back two videos and start at 6.26 and go through 6.26 and 6.27 before you come to look at this solution. So with that, the thing is that when you go down this first column or this first row, you see that there are just gaps, and gaps are just increasing in this direction, and gaps are increasing in that direction. So those are the things that we saw earlier in the previous examples, but in this case, because we introduced this zero, these are all negatives. The gaps were just negatives and penalties, right? There was no match here. This was just, you're inserting, deleting, and traversing one direction. So what you do is that you put zeros instead of the negatives that you're going to get from the gaps. So that's the first thing that you see, is that you would just insert zeros here, and then the same equations that you had before would be applied, except that you have this fourth condition of a zero, and you take a max of that. So now, like in previous solutions, we have the same stuff here, but we introduce this zero. So what does this mean? When you come from this direction, you would compute a value. When you come from this direction, you compute a value. This direction, you compute a value. And you introduce a zero here, and then compare all of them, and the max of those wins. So that's the only difference here. Otherwise, this algorithm is very similar to the previous algorithm. So now here's a worked out example. We fill these with zeros, and in my case, the scoring matrix is very, very simple. I assume if you match the characters on this and this, you get a +1. If you get mismatch, you get -1. If you get gap, it's -2. That's our scoring matrix. And then if you apply the scoring matrix, when you come from this side, when you come from this side, when you come from this side, you get -2, -2, and -1 respectively. -1 because you didn't match T and G. So you get this, and then the max of that with a zero put in alongside would be a zero. And so the next one would be when you want to come here, You can come from this side, which is a 0, you come from this side, which is a 0, and you come from this side, which is also a 0, then the respective penalties are a gap here -2, a gap here -2, and then this one is 0 plus a match, so it becomes a +1. And so you get a 1 here. And so if you work this all the way down, you will reach this point and you will fill this matrix up. The way I have written this is that, these are just the different solutions possible, and this is the final answer using the max and including the Smith-Waterman 0 in the comparison as well of the max. Now, given that we have solved this order mn matrix, what is the answer? What is the local subsequence that we were asked to find? And the local subsequence in this case is solved by doing the following algorithm. Once you have done this, you find the highest scores. And in this case, the highest score is 2. And it may not be in this right corner. It could be anywhere in this whole matrix, right? So you have to find the highest scores. And then from the highest scores, you walk backwards where they came from till you become 0. And when you reach 0, then that's the end, right? So in this case, you see that the A and the C are matched, and then it becomes 0. So the highest sequence was the CA. We also find a 2 here, and if you walk this backwards, you find a C and a T, a C and a T. So you find two sequences, both of size 2 inside this inside these two sequences, the DNA sequences, and you find two such patterns that were equal size, and so you would print them. So that is the Smith-Waterman algorithm. Again, this part is courtesy Wikipedia. You can go look up the Wikipedia. Just the link is very long, so I just put the. If you go on Wikipedia and search for Smith-Waterman, you should find and come to this page, and you can then look at these the nuances of this algorithm. But this algorithm, the deviation from the global alignment is that in this case, if you become negative, you just ignore from that point what the history was, because the zeros are meaningless. You only try to find where you're getting the positive alignments, which is if things match. And if things match and are significant, you stay on the positive side, then you keep that chain alive. If you go negative, then you basically cut off that chain and becomes 0. So you don't see pretty much wherever the long chains of discontinuities are, they become 0. So that's how this algorithm works, and dynamic programming obviously has been used here. And also the order of this calculation, as you can see, is order mn, because at each stage we did 4 computations to come up with this max here. So it's finite number computations for each cell of the grid, and then when you have this, you can then backtrack from any given max, and then find till you hit a 0. You backtrack to get the sequence of the alignment. So that's it, guys. This is solution to 6.28 local sequence alignment given to DNA sequences. Hopefully you enjoyed the video. If you did, give me a thumbs up or subscribe to my channel, and I will continue to bring you more dynamic programming solutions in the near future. Until that time, thank you for watching, and bye-bye.